Hi guys, please like, share and subscribe. And if you want full course for any actuarial subject, visit theactuarialguy.com or WhatsApp on this number. Thank you. Okay, so now I want to discuss with you a topic which extends across chapters. So it is first introduced in chapter number 14, which is what we are looking at right now. That is the binomial model chapter, and then goes on till chapter I think 18 is where this topic is last introduced, and this is called a state price deflator. Okay. So this is like an alternative approach to pricing of certain kind of derivative contracts, and let's see how it works and how it's different from the approach that we have been using so far. So let's just go back to our one period binomial model case, where we say that let's just say there's this one period and your V1, that is the value of the derivative at time 1 or the payoff from the derivative at time 1, is C1 if the share price goes up, that is S1 is equal to S0 times U, and CD if S1 is equal to S0 times D, right. This is the standard binomial model case that we used to have in one period, and then we used to price the derivative by just taking the present value. So by taking a factor of e to the power of minus r of the expectation of V1 under the risk neutral measure. So this was the risk neutral measure that we used to look at. That is why I have written it as Q. Okay, and this is the formula that we used to have, which is just taking the expectation under Q. So it would be Q times Cu. That is the probability that the risk neutral probability that the price goes up is Q, and the risk neutral probability that the price goes down is 1 minus Q times CD, and then it's being discounted. Perfect. So that's the idea. Now let's try to convert this to the state price deflator version of things. Okay. So now how it will work is, let's just take V naught, and it will be equal to e to the power of minus r. But what I'll try to do is I'll also try to introduce the real world probability along with the risk neutral probability. Okay. So the real world probability in this case is P. So what I'll do is I'll multiply and divide by P. So P times Q by P, okay, times Cu. So what I did is I multiplied and divided by P, okay, and then plus I'll multiply and divide by 1 minus P in the second term. So 1 minus P times 1 minus Q by 1 minus P multiplied with CD. Okay, so this is what we are looking at. I multiplied with the P on the first term, I multiplied and divided by P on the first term, and I multiplied and divided by 1 minus P on the second term. Okay, so that's what I have done. Now let me give you the idea of state price deflator. State price deflator is basically a contingent sort of deflator. We call it deflator because it's a discounting factor, and it depends on the state, basically whether the price has gone up or down, right. So the way this can be expressed, and the expression for the state price deflator is actually this discount factor along with this term. Okay, this term which is just the ratio of the risk free risk neutral probability to the real world probability when the price goes up, and the ratio of the risk neutral probability to the real world probability of the price going down. Okay, so how I can express this is, this can be written as the expectation. Okay, so let me just separate out the parts. What will I be separating out? Let me sign e to the power of r inside, so it will be e to the power of minus r times Q by P. Okay, this is one term, multiplied with PCU, okay, plus e to the power of minus r times 1 minus Q by 1 minus P, okay, and then 1 minus PCD. Okay, so this is what we have. This is the expression that I am looking at. Okay, and then this term, I'll show you what the state price deflator is. State price deflator is this term and this term. Okay, so this is what the state price deflator is. To put it in perspective, this whole thing can be written as, since you have the real world probabilities here, so it can be written as a real world expectation of the state price deflator times V1. Okay, so V1 takes a value Cu or Cd in respective cases, and I am multiplying it with this P and 1 minus P in respective cases. But I also have the state price deflator, which is this term and this term, which takes different values in different cases, whether the price goes up or down. So let's just call the state price deflator A1 as I have written it here, and let me define A1 as e to the power of minus r q by p in the case where the price goes up. So S1 is equal to S0 times U, and e to the power of minus r into 1 minus q by 1 minus p when the price goes down, S0 times d. Okay, so these are the two different sort of scenarios that we are working with, and these are the two different values. And then what I am doing is I am taking this state price deflator and the value of the derivative, okay, and I am multiplying it with probabilities under respective cases. So yeah, so that's how you are just taking an expectation of the product of the state price deflator and the value of the derivative at time 1, the payoff, and then you are taking the expectation under real world probability. And this is the other way of expressing the price. Okay, and just the difference, notice the difference here. The expectation was under the risk neutral probability, which is sort of an abstract concept. Here we are taking the expectation under the real world probability, which is better understood, and then we are introducing this concept of a state price deflator. Okay, so that's the idea. Okay, okay, so after this we have this super straightforward question which just asks you to calculate the value of the state price deflator, that is A1. This you can do. They've given all the data, they've given the share price, they've given the risk free rate of return, that is R, they've given that in one period's time either the share price can go up or down. Okay, so up is 120 and down is 85. So your U will become 1.2, D will become 0.85, and based on that they expect you to calculate the state price deflator. Real world probability is given as 0.6. Okay, so using U, D and R you can calculate the risk neutral probability, and once you have that you can actually calculate the value of A1 using the definition. So just look at the solution, it's super straightforward. Now they're stating a couple of things. So they're saying V1 is equal to 1. Okay, okay, now they're talking about a few particular cases. The first case is if V1 is equal to 1, that is the value of the derivative at time 1 is certainly equal to 1. Okay, if you have that sort of a certainty, then what happens is, in terms of your pricing, let me just show you. Yeah, in terms of your pricing, so V0, which is the price of the derivative at time 0, is just EP A1 V1, right? Now let me put V1 is equal to 1, so this will just become EP A1, right? Because V1 is a constant and that's just 1, right? And now what is EP A1? if I am to take the expectation of just the state price deflator, so it will be equal to, and you are taking the expectation obviously under the real world probability, so it will be equal to e to the power of minus r q by p under the real world probability. So the probability of this happening is p, plus e to the power of minus r 1 minus q upon 1 minus p, and the probability of this happening is 1 minus p. So this cancels out with this cancels out with this, and then you get e to the power of minus r q plus 1 minus q. This cancels out with this, so you just get e to the power of minus r. So if there is a derivative which always leads to a unit cash flow at time 1, then its current price will be e to the power of minus r, because it's simple. It's just that unit price of 1 pound discounted with a rate of r, so it becomes e to the power of minus r. That's it. That's how simple it is. Okay. There is no uncertainty around it, because the payoff is always 1. There is another case where it says V1 is equal to S1. What happens if V1 is equal to S1? So now the price of the derivative is same as the share, right? So how will that work out? Let's just see. So what is S1? S1 in these two cases is S0 U and S0 D, right? In both the cases. So here you will have S0 U, and here you will get S0 D, right? This is what you get. Okay. So now what will happen? P will cancel out with P. 1 minus P will cancel out with 1 minus P. E to the power of minus r S0 I will take common. Inside you have UQ plus 1 minus Q D. Okay, this is what you have. Now what is Q? Q is just e to the power of r minus u divided by u minus d, right? Let me make the substitution here, so it just becomes S0 e to the power of minus r u times q is e to the power of r minus u divided by u minus d, and then this is plus 1 minus this will be equal to e to the power of r minus d divided by u minus d multiplied with d. Okay, so this is what you get. Okay, now let's just open it up. So here what will happen is you'll get S0 e to the power of minus r, and then you have e to the power of minus r, e to the power of r times u minus u square plus one minus q. I think I've written it wrong. Q was equal to e to the power of r minus u minus d divided by u minus d, right? Yeah, this is what it was, right? So what will be 1 minus this? 1 minus q will be equal to u minus d plus e to the power of r plus d. Okay, this will be minus divided by u minus d. Yeah, so it will be u minus e to the power of r divided by u minus d. Yeah, this is what it will be, right? Now, once I simplify this, this becomes e to the power of r u minus u d plus u d minus e to the power of r d divided by u minus d, right? So this term cancels out with this term, and you have s naught e to the power of minus r and e to the power, and inside you have e to the power of r u minus d by u minus d. Okay, so this just cancels out with this cancels out with this, and you get s naught. Okay, so if the payoff from the derivative is equal to the share itself, that is s1, then the price of the derivative is equal to the share, which is quite intuitive, right? It's quite obvious. So these two things we have proved, right? If the derivative gives a payoff always of 1 unit, you get the price as e to the power of minus r. If the derivative gives a payoff which is equal to the share price, the price of the derivative is the price of the share. Okay, now let's just try and discuss this n period case, binomial lattice case. Okay, let's just get into this. Okay, so let's just talk about the n period case. So what happens in the n period case is that, you know, your share price can grow in each period by u or decline by d proportion. Okay, so that's how the n period case works, and ultimately your derivative, the payoff of your derivative v of n, depends on the price of the share at time n, that is Sn. Okay, and where Sn is nothing but whatever price of the share you started with multiplied with as many increases you had and as many decreases you had. Okay, so let's just say you know, you had I increases. There were obviously a total of n movements in n period, right? So what will be the number of decreases? It will be n minus I decreases, right? That makes sense, right? So your Sn can be obtained through this very simple equation. Okay, Sn can be obtained, and then Vn depends on this, right? Now how can I find V naught under our conventional pricing? We would just say that V naught is just equal to the discounted value of the derivative, the expectation of the derivative, the payoff of the expectation of the payoff of the derivative under the risk neutral probability, right? This is how we used to traditionally price without the use of state price deflator, right? This is the equation that we have seen all along, right? Where this Vn is obviously dependent on this Sn, which is just, you know, you start with S naught and then you multiply with the number of increases, and the number you multiply with the u as many increases you have and d as many decreases you have, so you arrive at this final price, right? And this is how you value it. So it's super straightforward, no problem. Now if I expand this can obviously be modeled as the binomial distribution, right? What's exactly happening is that you consider this increase to be a success and this decrease to be a failure, and that's how you can use it, use binomial probability to model it. So this e to the power of minus Rn will stay as it is. We'll sum from k, let's say, goes from 0 to n, where k is the number of increases. Okay, so the probability of any increase, the risk neutral probability is q, so q to the power of k, 1 minus q to the power of n minus k, that's the number of decreases, n minus k is the number of decreases. instead of I am using k. Okay, you can equivalently use I, okay, with the notation that I had used here. And obviously you have an nck, so nck q to the power of k 1 minus q to the power of n minus k, and then you are taking an expectation of Vn. So this is the probability of obtaining a particular value of Vn, which will be equal to Vn that will be obtained where there are k increases and n minus k decreases. So let's just write it as some value of Vn, okay, but which particular value? That value which is a function of Sn, which can be determined using this equation, which will be S0. You started with S0, but you had k increases and d to the power of d to the power of n minus k, and n minus k decreases. Okay, so what I have done essentially here is, instead of this Vn, I have substituted it with f of Sn, and Sn I have written using this expression. It's just that I has been replaced with k because that's the number of increases. Okay, so this is what you have, this is what you're looking at, and this is what they've given in the material as well, right? You can just simply write this expression as Vnk as well. Vnk, value of Vn, pay off from the derivative when there are k increases. Okay, now what you'll do is, you'll try to convert it to the state price deflator approach by bringing in the real world probability. So you'll divide by the real world probability and you'll multiply by the real world probability. So it just becomes e to the power of minus Rn, summing from k goes from 0 to n, nck, this stays as it is, q to the power of k. So I'll do q by p to the power of k, and then 1 minus q by 1 minus p to the power of n minus k. Okay, this is fine, but real world probabilities will again be multiplied, p to the power of k 1 minus p to the power of n minus k, and you can just write Vnk, value pay off from the derivative when there are k increases, right? Perfect. So now which parts will be taken into the state price deflator? Let's just see. So this is my probability, this is purely my probability, right? K increases and n minus k decreases. This is the real world probability of that. This part is just the payoff from the derivative, right? So now if I have to convert the whole thing into an expectation form, I have the probability, I have the payoff, but I also need the state price deflator, which is everything else. So this is just a different way of writing the price of the derivative. This is your price of the derivative, that is V0. So what you can write it as now is, you're taking the expectation under the real world probability. Notice that the probability I'm using is the real world probability of what? Of the state price deflator, which will be An and Vn, okay, and you're adding over all the possible values of k. So there can be 0 increases, 1 increase, 2 increase, 3 increase, so on and so forth, right? That's why you're taking an expectation, right? And what is An? An is just simply this whole expression. So it's e to the power of minus Rn, you'll have n increases, then q to the power, q by p to the power of k. Let's call it a random variable. Let's say the number of increases is a random variable called as nn. In n periods, how many increases you see? And 1 minus q by 1 minus p decreases. So this is just n minus n. Okay. So these are the parts that have gone into the state price deflator. Right. So that's fine. So this is how you write it. This is the expression for your state price deflator. Okay. And where nn is basically the number of it's a random variable. Here we were taking a particular value. Here we were taking a particular value, that is k, but here we are saying it's just a random variable for the number of increases. Okay. And if I want to write an in terms of an minus 1, so that will be equal to an minus 1 multiplied with, you will get 1 additional e to the power of minus r, because that would have been e to the power of minus r times n minus 1. You will get q by p if there is an increase, and you will get 1 minus q by 1 minus p if there is a decrease, right, in that particular period n. So you can indicate that with an indicator variable in and 1 minus in, and you can say that in takes a value 1 if there is an increase, that is Sn is equal to Sn minus 1 times u, and 0 if Sn is equal to Sn minus 1 times d. So what is exactly happening? You are just saying that if there is a decrease, then in takes a value 0. So this term comes in, this term goes away, right? Because in will be 0, 1 minus in will be 1. So an minus 1 to an you will have to multiply just this term, right? Similarly, if there is an increase, then in takes a value 1, this term goes away, this term comes in, okay, with power 1, right? So there will be an increase. Okay, so that's how it is working, not very complicated. And obviously you can model all the increases in the share price this way as well. Sn will be equal to Sn minus 1 multiplied with u to the power of in, d to the power of 1 minus in, right? And nn, that will be the total number of increases, can be modeled as k goes from 0 to n ik. Okay. So ik is basically whether you have any, it's the number of increase in one step. So if you add up the number of increases, total number of increases, that should give you nn. Okay. And by the same logic that we had discussed earlier, what will be equal to EP an times Vn under those two special cases. This is the price, okay, remember this is equal to the price of the derivative. This is how you price it. So the basic idea of this is quite simple. You are just taking an expectation of Vn as you always do, okay. Usually what you do is, usually you write V0 as e to the power of minus Rn multiplied with EQ Vn, right? This is what you do. But now you're not taking the expectation under the risk neutral probability, okay. This is your usual old expression that we were using before state price deflator. You are just taking an expectation under risk neutral probability. But state price deflator is just saying, if you want to take the expression under the real world probability, then what you need to do is that instead of the discount factor, you need to use a discount factor which is dependent on the increases or the decreases, dependent on the state of the underlying asset, right? So this is just replaced by this, and this was a constant, this was a constant, and this is basically not a constant. So this is a discount factor that depends on the state. State meaning where your share price is. That's the idea of a state price deflator approach, okay. That is why we use it, so that we can discount based on the real world probability, which is a more realistic measure as compared to the abstract measure, that is risk neutral probability. Okay, this said and done, what are those two special cases? Okay, what if Vn is always equal to 1, okay. What if Vn is equal to 1? Then this V0 will become expectation of An, right? And if you will take this will just come to be e to the power of minus Rn. That is, if a derivative always gives a payoff of 1, its price has to be that payoff discounted for n years, and there is no risk. This is certain payoff, this is certain, right? So yeah, that's fine. And then again, what is V naught equal to? So this is case 1, where Vn is equal to 1. Okay, so V naught will be this. What is the other case? Case 2 will be, what if the payoff is always equal to the share price? Then we have discussed this. Your price, if the derivative just pays the share price, then the price of the derivative should be same as the share price at time 0. So that's how it works. Okay. So this is something. Okay. And finally just one thing. So far what we were trying to do is we were trying to find the price of the derivative at time 0. Okay. So how you are doing that using the state price deflator approaches? You are just saying that let's take the expectation of the derivative under the of the payoff of the derivative, but let's just discount it using this state price deflator, right? But what if you want to get it to certain time t? Okay, then you take this, but you also divide by an AT, that is the state price deflator value at time t. So to discount, you were multiplying with the AT. Okay, so you, but if you want to accumulate to time t, so you divide this whole expression by a small t. So you are accumulating till a time a small t, and this will give you Vt. Okay, so this is the idea. So this is all that is covered in this topic of state price deflators. Okay, so let us try to prove this result mathematically from first principles. Okay, so your usual pricing approach when you are trying to calculate Vt, it's nothing but you take the payoff from the derivative at time n, right, which is like the time of maturity or like the last point of time, given the filtration at time t, that is given all the information up till time small t. Okay, here instead of capital T I am taking n, right? Yeah, or we can just replace the n with a capital T. So let me just use this same notation. Yeah. So this is what I have. So the final payoff is at time capital T, and that payoff from the derivative is C capital T. Given that information up till time t, you want to find the price of this derivative at time small t. Okay, that's what you want to do. So now what you will do is you will take the payoff at time capital T given and you will take its expectation under the risk neutral probability given the information up till time small t. Okay, and then you will discount that from time capital T to time small t. That's the simple logic. Okay, let's just try to understand that how it would work in terms of the binomial cash flows or the binomial tree cash flows. So let's just see. So your share price at time small t can be written as ST. Okay, this is known at time small t. After this, let's say there are k upward movements and the total duration, the total number of periods is capital T minus t. So the number of downward movements will just be capital T minus k. Okay, so I am saying total movements is equal to capital T minus small t. Then upward is equal to k and downward is equal to capital T minus k. Okay, right. So that is what is happening, and this is basically you can write this as the notation that we used to use for this was Vn given k upward movements, right. So this can be written as f of Vn for k upward movements, right. That is what you can write it as, right. Okay, and then we need to take the probability of k upward movements, which is t minus t ck. So k upward movements are chosen. The risk neutral probability of k upward movements is q to the power of k, and the risk neutral probability of t minus k downward movements is 1 minus q to the power of t minus k. Okay, this is what is happening. Now let's apply the state price deflator approach, and this equation I have just taken from the material. So you can actually find this equation given on page number 32 of the chapter. Okay, yeah. So we have seen this equation before, right? So now I'll apply the state price deflator here, which is just try to get the real world probability here. So e to the power of minus r capital T minus small t. Okay, summing over, k goes from 0 to capital T minus small t, v and k. Then you have got q to the power of q by p to the power of k, 1 minus q by 1 minus p to the power of t minus k, and then you have t minus t c k. So, and then multiplied with p to the power of k, 1 minus p to the power of t minus k. Okay. Now, this is the real world probability of having k upward movements. Okay, and this is the value of your state price deflator. Okay, sorry, this along with this. Okay, and then this is the payoff from the derivative. Now you want to get it in this form. This is the form you want to get it in. So what I can do is, let's try to convert it into this form. So let's multiply with let's say we are saying that from time small t to time capital T, there are k upward movements, right? And t minus t downward minus k downward movements. But this is something which is going to happen in the future. We don't know if this will be the numbers. These are just arbitrary numbers, and we are anyway adding over all the possible values of k. But for the past, we know we would have known what is the number of upward movements that would have occurred and the downward movements that would have occurred. Let's say in the past, in this t years, there was I upward movements and t minus I downward movements, right? Plausible, because the total number of movements is t. So I is known to be the number of upward movements, right? So now what I can do is, this term remains e to the power of r t minus t. Okay, let's do one thing. Let's copy the whole thing. Let's select this. Okay. So now let's just multiply and divide by the state price deflator up to time t, at and at. Okay. So if I do that, let me write it here itself. What is the value of 80 is the question. In the denominator, I'll leave it as 80. In the numerator, I'll write the exact value it takes. So since there have been I upward movements, the value of the state price deflator will be Q by P to the power of I and 1 minus Q by 1 minus P to the power of T minus I. Okay. This is what I can write it, this part as, and obviously multiplied with e to the power of minus R T, because I'm discounting for T years. Okay. Now let's just combine the whole thing. So it will be e to the power of minus R T minus T multiplied with this term. So it will become e to the power of minus R T. Okay. Summing over, K goes from 0 to T minus T. Okay. V and K. This can be added with this. So this is Q by P to the power of I plus K. Okay. And this will become 1 minus Q by 1 minus P to the power of, this was T minus K, right? So this T will get added. So it will be capital T minus I minus K. And then multiplied with T minus T C K, P to the power of K, 1 minus P to the power of T minus K. Okay. And the whole thing divided by 80. Now, if you see, and this should be Vt, because there is no n. So now if you see, you have the state price deflator here, which is known. You have the state price deflator, which is known. In the numerator, you have the probability of K upward increases occurring after time small t. That is, from time small t to time capital T, there are K upward movements, which is the only uncertain thing. In terms of the state price deflator, you have two parts of the state price deflator. One part is based on I upward movements, which are known. So that's a constant part. And then, because this is in the past, K upward movements, which is unknown, right? So what can I write the numerator as? I can write it as expectation under the real world probability, because you have the real world probability of K upward movements occurring in the future, which is this whole thing, T minus T C K, P to the power of K, 1 minus P to the power of T minus T minus K, right? This is the binomial probability of K upward movements. Then you are multiplying it with two things. One is the price of the derivative itself, or the payoff of the derivative at time capital T, and then multiplying it with the value of the state price deflator. Given the fact that there have been I movements in the past, I upward movements, so these three terms pertain to the state price deflator. I upward movements in the past, and there will be K upward movements in the future. So the total number of upward movements just becomes I plus K. Okay, that's the total number of upward movements that you have. So this is what these three terms comprise of your state price deflator, so that becomes AT, and then divided by small at, and this is your VT. Okay, so that's how you show this mathematically.